Okay, so we're going to talk about some special matrices, and I want to talk about addition and multiplication of matrices when we're putting them on top of each other. We've talked about multiplying a vector and the matrix multiply that goes along with it, but you can also add matrices together, and you can multiply matrices times each other, building on top of those operations over and over again. So we've already seen a couple of examples of that when we were talking about the inverse, because the inverse is really the multiplication. The inverse times a matrix is really the multiplication of those two matrices, equaling something called the identity matrix. So here's our standard equation that we're thinking of. So m times v, and I could have broken m down into two different matrices. Suppose that was convenient. And both of those would act on v. And because this is a linear operation, I actually know that that's equal to both of them acting on the vector separately. Okay. Matrix addition, in order to make this true, means that the addition of two matrices is just adding every single one of the components to its partner in the same location. You don't combine the different components from different rows and columns together, but you just add, say, the ith row and the jth column of this to the ith row and the jth column of this, or you could distribute it out this way. If that's the case, then this will be equal to this in general. Now, along with this addition of matrices, there's a special matrix, the additive identity matrix, which is just a big old zero matrix. So if one of these two matrices was the zero matrix, then the answer of that combination is just gives you back the original matrix you had. It's true when you're multiplying by the vector. It also would be true component by component. So the zero matrix is just a matrix that's the same size as whatever you're adding it to, with all zeros in all of the locations. And I can swap the order of these because the addition in each of those components is commutative. And so I can commute the operation of the two matrices like that. All right, what about multiplication? So in the case of multiplication, we have something different. When we multiply together two matrices, like our base example here is actually the multiplication of a vector and a matrix, or it could be two different matrices. The only thing we've really talked about is that the number of rows of this matrix is the outcome of the number of rows, and the number of columns of this matrix is the outcome of the number of columns of the product, and then the number of columns here has to match the number of rows here so that we can do our little patterned multiplication step by step to get that part out. So can I just consider whether this is commutative? Does matrix multiplication commute? Let's just write it down and see what the problem is. Well, suppose these two were not matched. So suppose this was 2 by 2 and this was 2 by 1. Now this is 2 by 1 and this is 2 by 2. The 1 and the 2 don't have the right amount to equal each other. So just writing it down at first pace, we may not even be able to use the definition of matrix multiply if we reverse the order. So it definitely is not the case that matrices commute. We did talk about one exception to that. I could transpose both of these matrices, and that works because the transpose, if this is 2 by 1, this would be 1 by 2, this is 2 by 2, this is 2 by 2, then this would be 1 by 2, 2 by 2. That would work for the matrix multiplication. And in fact, we talked this through, you actually get exactly the same equations if you do it that way, just with all of the rows swapped for columns. So the transpose of the product of the transposes is equal to the original system. So this is just equivalent. These are the same operations. So the matrix transpose is another special matrix, and that's the one where you just switch all the indices, or you mirror reflect across the diagonal of the matrix. What else have we got for special matrices? Well, we actually have the matrix inverse as well. So we use the matrix inverse in equations that look like this, and we said V is equal to the matrix inverse times X, but really that's skipping a step. That's like dividing through by the matrix. But we could have also written it equivalently as the matrix inverse times the matrix on the left side. And because multiplying by matrices doesn't commute, we have to be careful whether we're multiplying from the left or multiplying from the right, times the vector is equal to the matrix inverse times this vector. So I took this equation, I multiplied both sides by the matrix inverse on both sides, from the left on both sides. What's this equal to? Well, we see that this operation has to give us the same value as that. That's what we were assuming before. And if this was just simple multiplication, we would say that something times its inverse is equal to 1. Turns out that's not quite enough to do it with matrices. We have to introduce a new matrix, which is called the identity matrix, which is a matrix that looks like this. It has 1s along the diagonal, 0s off the diagonal, on all the spots that are equal to 0. And if you go through and multiply this times something on either its right side or its left side, you end up with the original matrix that you got started with. The identity matrix has to be square because the inverse matrix has the same size as the transpose matrix. So the matrix inverse times the matrix is equal to a square matrix, as is it swapped around the matrix right multiplied by the matrix inverse. So we can write a bunch of things like this: matrix inverse times matrix. And I also could say that M times the identity matrix is equal to the matrix, the original M matrix. This is true for any matrix. It's not like the eigenvalues. This is true in general. Or I could do it the other way around and put the identity matrix on the other side. Or I could do this other one. I could say the identity matrix is equal to the matrix right multiplied by its inverse matrix. Okay, so that's the identity matrix. So we have an additive identity, the zero matrix. We have a multiplicative identity, which is the identity matrix. We have the transpose of a matrix. We have the inverse of a matrix. The last sort of interesting notion is that there's a special matrix called orthogonal matrices whose transpose is actually equal to their inverse. And there are other matrices whose complex transpose, so flip all of them, and then take the complex conjugate of every element, is equal to their inverse. Those are called self-adjoint matrices.